Okay, good morning everyone again. I think we can get started now. Webinar is scheduled to start at 10:05 Pacific time and 1:05 Eastern time. So I hope everyone is ready to go. I can still see there's people logging in, but we will stick to the schedule and try to go ahead right now. I assume you can all see the screen and hopefully my mouse moving. So we will get started. First, I will be your presenter today. My name is Max Klosen. I'm a timber engineer here at Mightycon Timber Connectors. Mightycon is a small firm based out of Vancouver, British Columbia, Canada. We specialize on modern timber connection technologies, which is one of the major parts that are coming up in the industry, looking at all the tall wood buildings that are popping up in the United States and Canada. We are specializing in these particular buildings. My background is timber engineering and timber framing, so I have completed a carpentry degree and timber framing degree in Germany and also an engineering degree from Germany before I came to Canada about 10 years ago. Since then, I have studied at the University of British Columbia in timber engineering with the focus on the seismic performance of moment-resisting timber connections and CLT connections. And right now we are still engaged in some research projects that involve CLTs, and part of this involvement will be presented today in the webinar. So we will basically have a refresher on the performance of CLT connections under static loading, which was presented earlier in 2015. The webinar is still on our website, and the slides as well, and the design guide. So if you want to take a look at these pieces of literature later, you are welcome to join the website and take a look at those. Today we are focusing on the performance of CLT connections under cyclic loading. After the research project at UBC here in Vancouver was completed, and then lastly we'll provide a summary of the proposed design procedures and design values. The first campaign was on static loading. We investigated the capacities of panel-to-panel connections, such as surface pline, half-lapped, and butt joints. In the second campaign, we looked at the cyclic performance of these systems, again in panel-to-panel connections, surface pline, half-lap, butt joints, and so on. And lastly, we will take a look at the data, the results that we obtained, some of the statistics we want to present, like drops in capacities between static and dynamic loading, how load displacement curves look like, ductility estimates, capacity estimates, failure modes, and so on and so on. As usual, we want to put a disclaimer on our information provided here. The webinar is for informational purpose only. This is because we have only done small test series here of 3 replicates or 6 replicates, depending on the series. However, we do strongly believe that we can use this test data to verify existing or future code provisions in CLT connection design through this small sample test series. Test campaign number 1, static loading. As mentioned before, we focused on surface pline joints, half-lap joints with a variety of fastener layouts, and also butt joints with a variety of fastener layouts. Surface pline, half-lap joints, and butt joints are all listed here to the left-hand side. The label SS is basically surface pline, and then in a 3-ply panel with 90-degree screws. LJ is lap joints. A whole bunch of different lap joints were tested, and BJ is butt joints. We have a variety of different angles. We have 90-degree angles, 45-degree angles, and a combination out of 45 and 90-degree screws, and also compound angles of 30 and 45 degrees in one specimen. A variety of different numbers of screws were used, ranging between 8 and 12 screws per specimen. This is basically determined by the spacings and an edge distance requirements that we have used for the specimen. We have used fasteners in shear, fasteners in withdrawal application, and interestingly, with results that we see a little bit later, we have used fasteners in shear and withdrawal combined action. All tests were performed in cross-lam CLT panels, V2 M1 grade from a local manufacturer here in British Columbia. Our test setup was selected according to DIN standard 26891, which is basically an actuator pushing down onto our specimen. The specimen is on a small, about 15-degree angle to subject the fasteners to a pure tension load. What we basically do in our loading, we load the connection up to 40% of its ultimate expected load. Then we unload the specimen to about 10% of its expected load, and then we ultimately break the specimen until ultimate failure occurs. Some of the failure modes we want to summarize that we saw in the static testing. Here we see surface pline joints. Surface pline joints, we see fastener yielding, head pull in, wood crushing, tearing of wood fiber, and out of plane rotation, which we simulate and showcase in this picture here. For the joints where we have half-lapped panels, that was on one hand fasteners in shear, on the other hand fasteners in withdrawal. We have fasteners in withdrawal on the outside, fasteners in shear on the inside, and then again withdrawal on the outside. Failure modes that we saw here are again head push in, head pull in, fastener bending, splitting of the wood fiber, and out of plane rotation for some of the specimen. In this table here, we present a summary of all test results. There is a lot of numbers presented here, which we will not go into detail now in this webinar. However, you're welcome to take a look at these slides after the webinar. I'm pretty sure these slides are going to be sent to you by email today or tomorrow if you have registered for the webinar, and you can have a look at these capacities, yield modes, ultimate displacements at yield of the fasteners, and stiffnesses and estimated ductility values of the systems. One particular mention that we want to do is we have basically looked at connection layouts with friction, and then the NF specimen is without friction, no friction in the specimen. To do that, we basically have placed a non-friction layer or barrier in the shear plane that is meant to reduce the friction. However, what we do see as an impact here is there's no real significant impact for specimen that have friction and specimen that have no friction throughout the entire test series. How this looks in the load displacement curves is what we see here. So the bottom curve, this one here, is basically a fastener in a surface pline shear connection with and without friction. As we can see, there's not a lot of difference in those connections, and the same applies to the half-lap joint, which we see here. There's a very small difference only between the specimen that had full friction and had no friction in the shear plane. The third test setup is fasteners in tension action. So we are placing the fasteners at a 45-degree angle to the force application, subjecting the fastener to a tension force. For these applications, we use fully threaded wood screws. I will explain a little bit later some more details about these fasteners. What we see now is that we get a much stiffer connection with a lot less ductility. So compared to the 1.5 inches of ultimate displacement that we see in the static testing of the shear connection joints, we now only see about a 1/4 inch maybe of deflection or deformation in our connection system. In the third layout, we have looked at the capacities and the performance of systems with combined action. So we basically have fasteners in tension, which are those ones, and fasteners in shear, which are those 4 fasteners. So we have a combined action of our system, fasteners in tension and fasteners in shear. This is what we see in this green load displacement curve. So the fasteners in shear in tension are pretty much acting similar to the pure tension joint. They are almost equivalent to that load displacement curve. We get a very linear increase in capacity and stiffness. And then as soon as the tension screws fail or start failing, we transfer the load to our shear fasteners, and the shear fasteners pick up the load and provide about 1 inch of deformation in our connection before it ultimately fails. So again, a quick summary here. We have fasteners in shear, STS, stands for, which we see here, STS stands for self-tapping wood screws. Those screws do not need any pre-drilling. We have basically self-tapping wood screws in shear in the surface spline connection and the half lap joint. We have fasteners in tension. Those are fully threaded screws at 45-degree angles to the shear force. And then we have fasteners in a combined action, self-tapping screws on 45 and 90 degrees in the same specimen. In this plot, we show the difference between the three-ply panels. So this one here, and that one here, and this one are all test results from three-ply panels. CLT panels or cross-laminated timber panels come in a variety of layups, typically 3 layers, 5 layers, 9 or 12 layers, depending on the loading you have on them. With the thicker panels, you obviously get more penetration of the fasteners into it and achieve much stronger connection systems compared to the thinner panels. In this table, we want to basically give a little bit of insight on the stiffness analysis that we have done. The stiffness was analyzed for these tests in the 10 to 40% range. So in the initial start of the testing, basically, those are the stiffness values at this level that we get for this system. There's no clean guidelines, at least not to my knowledge, on where to evaluate the connections for design. It could be at the 0.4 level, which is 40% of the ultimate load, maybe 0.7, maybe 0.9. Maybe it also depends on what you really want to do with your connections and where you design them. We also want to basically take a look at the combined connection assemblies where we have fasteners in withdrawal, shear, shear, withdrawal, and fasteners in shear, withdrawal, shear, withdrawal, shear. So these connection systems give us a very high ductility and a very high stiffness, high capacity out of the system. So this seems to be the ideal solution for what we are typically planning on doing. Here we see a summary of the 5-ply specimen. The 5-ply specimen, as mentioned already, give us more embedment for the fasteners and hence we get more capacity. However, we do not necessarily get higher stiffnesses, which we already see in those values. However, we will also run a comparison later on the cyclic loading tables. A comparison between 3 and 5-ply on the maximum force level, we basically increase the capacity between 3 and 5-ply panels due to the previously mentioned facts of more embedment, more pull-out resistances, and so on of our fasteners. In terms of stiffness, we do not see an increase between 3 and 5-ply necessarily, only in the surface spline and the 45-90-degree screw layout down here. We see increases. In all other systems, we see a drop in stiffness. We do not quite know why this is yet 100%. We do have some mechanical models for this and ideas on why this is. However, this needs to be verified before it is mentioned. A comparison here quickly on the predicted design loads and the overstrength factors. So in those two columns, we have our prediction based on current design standards presented in the American Wood Council CLT Design Handbook or the National Design Standard, NDS. In the bottom here, we see this in a more graphical fashion. So we can definitely see that all our green bars, which are our static test values, compared to the gray bars, which are our static design reference design values, considering the CD factor of 1.6 for short-term load duration, we have pretty conservative results throughout the entire test series. Now we had a quick 10-minute review of the static loading testing on our CLT connections, and now we want to move into the cyclic loading procedures. We basically have used the career loading procedure, which is a standard loading procedure for seismic loading in North America. One problem with our test setup here was that we basically created the prying force in this area here. When we push down, we create a compression here, the prying force goes away. However, if we pull up in this direction and apply a tension load on our connection, we do create a lateral force component here that is trying to pry the specimen apart. We did not think of this properly before we were doing the testing. We will do verification testing on this. However, we still believe the results are very valid in what we want to show and want to do. If anything, they should be more conservative because the fastener is subjected not only to a vertical shear load, but also to a shear load in this direction and a combined shear action in two directions. We basically have again tested surface spline, half lap joints and butt joints with the previously mentioned 90 degree, 45 and screw in angle combinations of 45, 90 and 33, 45 degrees. Again, there was a variety of self-tapping screws per shear plane, depending on the specimen configuration and spacing and edge distance requirements. Also, fasteners were again subjected to plane shear forces, withdrawal forces, shear and withdrawal forces in a variety of specimen. All these cyclic tests were again performed in cross-lamp panels, V2 M1 grade. This is the standard grade panel that we were getting from the manufacturer locally here in BC. Here we have a look at the first connection setup. We have a traditional surface pline joint. We are using 5/16 by 3 1/8 wood screws at 2 inches of thread length. Those screws are ICC approved and are standard fasteners for CLT connection systems. Here we see the first cyclic load displacement curve of this specimen. What we can clearly see is we have a difference between our green cyclic curve, which we have here. This is the cyclic test result for the surface pline connection with 90 degree screws. 90 degree screws means they are driven in perpendicular to the face of the CLT panel in the main span direction basically and subjected to a pure dowel action or shear force. The gray curve here is always our static load displacement curve plotted against the dynamic load displacement curve. In the negative cycle here, because the static loading is only in one direction, we have just plotted the positive load displacement curve of the static loading into the negative area to have somewhat of a reference between positive static loading and positive cycle and static loading and negative cycle. So this curve here again is just the mirror image of the positive curve. Here we always plot the backbone curve, the cyclic backbone curve, which is the red line here. The backbone curve is basically connecting the tips of the maximum load or ultimate load of each applied load cycle with a line, and that gives us the backbone curve. Here we can nicely see the differences between the static and dynamic curves. We do see a quite significant drop in capacity from the static to the dynamic loading. So this is what we typically expect under dynamic loading. We do expect a smaller capacity due to a variety of failure modes that happen in these connections. Failure modes that we observed are, as mentioned, pulling apart the specimen or prying it apart due to the tension force in the tension cycle, tension force in this direction. We also saw a lot of wood crushing in these areas, fastener breakage due to low cycle fatigue. We need to remember that these fasteners are case hardened to provide a high bending yield strength. However, they do not perform very outstanding like mild steel would do. They have typical low cycle fatigue. So if we apply 15 to 20 load cycles to them and bend them back and forth, they will break eventually. However, as we saw in the load displacement curves, this happens at fairly large displacements. The next setup we have used is the half lap joint. We basically are just simply cutting a half lap into the CLT panels and then fastening the CLT panels back together with self-tapping wood screws. We are again using 5/16 by 3 1/2 inch wood screws. For these systems, we have about 2 3/8 of thread length, which is slightly extending past the shear plane, not ideal, however suitable for this testing. This is also a standard ICC approved fastener that we use for these systems. The load displacement curve that we obtain from this testing is shown here. Interestingly, we do not see a lot of difference in the linear ranges here. Static and cyclic testing are pretty much equivalent in this area. We do see a little bit of tapering off here in the negative load cycle, and then obviously in the higher load ranges we do see quite a bit of difference between static and dynamic loading. However, what we also see is that we get at least 1 inch of displacement out of our system here, so that is definitely considered a significant amount of deformation while we are maintaining our load. We need to remember that for design purpose, our load is probably in the design range somewhere around here, maybe at the most at 500 pounds. I believe it's at around 280 pounds for this particular connection if we were to use the standard design procedure from the NDS. The backbone curve confirms these results. We have almost equivalent performance in the positive cycle here and a little bit of tapering off in the negative cycle. However, the curves are very similar. In the ultimate ranges, we do see a capacity drop and performance drop again between cyclic and static loading. In terms of failure modes, we see similar failure modes here again. We do see prying apart and moving apart of the CLT connection in the horizontal direction here. This is again due to the prying force that was created. We do also see a significant amount of wood crushing. Actually, we form a nice cavity here behind our screw. So the screw was basically pushed from here all the way to that side, and then in the next cycle, in negative cycle, it would need to go through that cavity back to that wood, crush the wood fiber a little bit more, and move in the other direction again. Interestingly, what we see on the right-hand side here, the fasteners are pretty much bending to a 45-degree angle, and then at one point, of course, they will break due to low cycle fatigue or crush the wood fiber, pull in the heads up top here, and so on. However, very interesting here again, the screws are bending to a 45-degree angle almost, which is one of the manufacturing requirements for European fasteners. The fasteners that we have used were made in Germany. So they are basically required to bend by 45 degrees without breaking. Another half lap joint that we have tested is with 45-degree full thread wood screws in tension. So we are driving in the wood screws at 45 degrees in two opposite directions to create pairs of screws. Basically, when we subject the specimen to loading in this direction, we basically have some of the fasteners here in tension and the other ones in compression, and we do assume that tension and compression screws takes the same load. There's scientific evidence for that as well, and the mechanical models confirm it also. So we confirm that self-tapping wood screws in tension and compression take the same load in our testing here. We have used 5/16 full thread wood screws. These fasteners basically are threaded all the way from the tip to the head to provide embedment and high pull-out resistances in the lower area here and in the upper area. We have used 12 of these fasteners in the shear plane and around, this is in a metric unit here, 140 millimeters, 5.5 inches. How the load displacement curve looks like, we see here. So compared to the pretty much very ductile systems that we have seen before for surface pline and half lap joints, we see a much stiffer performance here. It's almost a vertical linear line going up to around 1,500 pounds of loading. These values are per screw, so 1,500 pounds roughly ultimately were taken per screw in this test setup. We do see high stiffness and high capacity out of the system. However, we only see about ½ inch of ultimate displacement in positive and negative cycles. The backbone curve confirms this again. We have a linear increase in static and dynamic loading here up to a certain point, and then the fasteners fail. We do again see a capacity decrease between static and dynamic loading of these systems. In terms of failure modes, we see again prying the specimen apart. We see head push in, head pull out, which we nicely see in this system. So we can nicely see all the wood fibers that were torn out, pushed out, and then in negative cycle being pushed in. We can also see that the screw is almost bent vertically. It was at a 45-degree angle before, so we do also get fastener bending and yielding out of these failure modes. Here we see the typical failure head pull-in of the fully threaded screws, which is very often observed in these ultimate stages of the specimen. The next joint is one of the more special joints where we want to combine fasteners in shear and fasteners in tension. So in this setup, we have placed the tension fasteners in the outside of the specimen. So basically towards the load application happens from up here. So the fasteners in tension were placed in this area and in that area, and then fasteners in shear were only in this particular area here. So what we are hoping to get out of these test data and fastener setups is pretty much the effect of high strength, high stiffness, however with ductility, which is a typically rather hard failure mode to achieve, and only a few systems can do it. Here we want to play a quick video for you on these test setups to see how much deformation the systems get. I do believe you cannot hear the sound of this video, but there is lots of wood crushing sound and machinery noise, obviously, from the actuators of the test rig. We can see quite a bit of displacement in the positive cycle and then in the negative cycle. We can also see how these compression screws here are basically pushed out of the specimen now, bent over. We zoom in a little bit on this to make this clearer for you. So here we see how the screw is pushed in and pulled out in the ultimate stages of failure for the specimen. Going to the next slide, we see the load displacement curves, again static plotted against dynamic loading curve. We definitely have similar performances in the linear ranges here at around the 500-pound design mark. There's very little difference between static and dynamic loading. The same basically happens in the negative load cycle here. And then very nicely, we see a lot of ductility in our system. We basically maintain the load all the way up to almost 1.5 inches, we would say, in terms of design load. Remember, our design load will be somewhere down here. So we have at least a safety factor of 2.5 in our system here, while we are maintaining about 1.5 inches of displacement in our cyclic loading. The backbone curve again shows these results nicely. We do have again a significant drop between the static loading curve and the dynamic backbone curve, and we do see the displacement of 1.5 inches nicely. Overall, failure modes and connection performance is as we see here. Again, we create prying forces, pry the specimen apart, and then ultimately we see push out and pull in of fasteners. We can see a big hole here where the fastener has pulled in and pushed out a lot of wood fiber in the depending cycles. And here we see after the specimen was taken apart, there's lots of wood broken off, lots of wood fiber sheared out, fasteners are bent over and have yielded. The second setup that we have used for the combined fasteners, we basically have shear fasteners to the outside of the specimen. Again, remember, load application was happening in this direction. Before we had tension fasteners, so 45-degree screws in this area, and then we had shear screws in this area and tension screws in this area. Now we have the exact opposite setup. So what we have now is we have shear fasteners here and then tension screws here, another set of shear fasteners and then tension fasteners, and then again shear fasteners down here. Again, we wanted to see what the difference between those connections is, and as we see here in the load displacement curves, we do see a difference. The other connection system basically performed not as this one. The previous connection system had a big difference in static and dynamic loading. Here we see again a fairly similar performance in the linear ranges here between static and dynamic loading. This is also again confirmed in the in the backbone curve of the cyclic testing. We do see capacity drops, however they are not as significant as we have seen it here. This was the previously shown specimen, so we can clearly see capacities are in similar ranges as we have for the other system. They are in the exact same range at around 1,000 pounds when the specimen starts failing. Similar, we have it here at around 1,000 pounds. This particular setup here goes a little bit higher in ultimate force compared to this one. Ductility wise, they are probably in the same ranges between 1 and 1.5 inches of displacement before failure is observed. Ultimately, failure modes here look again very much the same compared to what we had before. We get push in and pull out of the fasteners, lots of wood fiber crushing and being pushed out for the tension and compression screws. And again, we see the prying force that is acting and prying the specimen apart. The next specimen here, interestingly, has 45 and 30 degree screw-in angles. So we have driven in the fastener on a compound angle, which is load application again from the top, and the fastener is driven in like this and like that, and the ones at the bottom up from this direction here, and this was driven down there to create tension and compression screws again and tension loads on the tension fasteners. Another advantage that we see here with the system is that we can basically transfer out of plane forces. So if we have panel joints that are not bearing on a beam, we would be able to transfer loads in the vertical direction, gravity loads for instance, because the fasteners are at an angle to this particular force, and that subjects the fastener to a tension force in this direction too, and we are able to transfer loads out of the plane. Load displacement curve of this specimen looks as we see here. We see a very linear increase of stiffness up to capacity up to around 1,000 pounds. I would say this is a very predictable fashion and performance for all the connection layouts that have tension screws in them. They're always very linear to around 1,000 pounds, which is in this area, and then they start to taper off. Some of the load cycles here in the dynamic loading actually exceeded the static capacity, which is definitely possible, however not common. Looking at the backbone curve, we see similar fashions here. Again, it is very equivalent to the static loading curve. So for this particular connection setup, the static and dynamic loading does not seem to have an impact on it. Ultimately, in terms of failure modes, we see again prying a part of the specimen, rotation out of plane and in plane, and we see lots of yielding of the fasteners here in ultimate stages. What we see in this area here, we basically have a screw driven in that way, and then it has bent, I don't know, 30 degrees maybe over, or 45 degrees even, and yielded in this area here. And it has also, what we see here, initially it was driven in here in this area, and it basically pulled out about an inch maybe out of the wood fiber in this direction, which ultimately led to the failure mode here. We do also see failure modes such as head pull in and head push out. What we see here, those compression screws are basically pushed out, and again they have bent over on an almost 45 degree angle here, which we see to their original position. Overall, this connection exhibits a reasonable amount of ductility and stiffness overall, because we consider this as a very stiff and rigid connection, and we still get about half an inch, 3/4 of an inch displacement out of the system. The last connection setup that we have used is a plain and simple butt joint. We do see a variety of advantages for this system. First of all, in this particular area here, we do not need to do any fancy machining. We just need to cut a square edge and then butt joint the panel into that direction. We may also be able to transfer gravity loads on these systems. It will be rather small, but there is the potential of transferring gravity loads in this direction. And then also, of course, shear loads in this direction here. The fasteners are again fully threaded wood screws, 5/16 by 5.5 inches, driven into that 3-ply cross-lamp panel. Load displacement curves of this look like we see here. The static curve performs similar to the dynamic curve, where the dynamic curve actually exceeds the capacity of the static load displacement curves. not something that we commonly see. It is definitely the case in the positive load cycle. In the negative load cycle, if we just mirror the positive load cycle, we see a little bit of dynamic loading decrease, which is also very normal. Looking at the backbone curve, we do see the capacity gain that we have in our system. So again, cyclic capacity of this particular setup is stronger than the static performance of the system in our particular test setup. Ultimately, the failure modes are again prying a part of the specimen. What we see here was about 1/2 to 3/4 inch of displacement or separation of the specimen. Displacement in this area was actually around 1 inch or 3/4 inch as well. And then we nicely see fastener yielding, bending of the fastener, and crushing of the wood fiber respectively. Interestingly, again, we are pushing these fasteners up and down. So basically up and down in this direction. That subjects our fasteners, which are driven in plane shear action. This way, basically, as soon as the connection deforms, we can basically see how the connector deforms as well. So the connector was driven in originally like this, and then it tapers off like that at a 45-degree angle or more during the ultimate stages of the testing. This again, when we look at the mechanics here, when we apply a vertical shear force and have a fastener driven in or deformed at an angle to that grain, we again subject the fastener to tension or compression loading here, which may be one of the reasons why these systems have so much ductility and still maintain a lot of capacity out of the system. We need to keep in mind, if we analyze this, that fasteners in withdrawal action are always much stronger and stiffer than fasteners in shear action. The simple example for that is, again, when you put a wood screw into a piece of wood, it's easy to bend it over. However, it is rather hard to pull it out. And for these engineered fasteners at 1/4 inch up to 1/2 inch or even 9/16 in diameter, you can imagine you get very significant pull-out forces and pull-out capacities for these systems. The next slide shows again low cycle fatigue of these systems. So we have breakage of some of the fasteners. There's 8 fasteners in this joint, and ultimately 1 out of 8 fasteners broke apart after experiencing low cycle fatigue. We also get some head pull-in and push-out, which is due to the tension forces. We do see a lot of wood crushing in the center layer here throughout the entire connection series, which is an indicator for a potential energy dissipation in the system. Now, in the next few slides, we want to present a summary of all the load displacement curves with surface splines, half-lap joints, and so on. So again, the first backbone curve that we see here is for the cyclic loading of a surface spline. Against this, we have plotted the performance of a surface spline in a 3-ply panel with 90-degree shear screws. Against that, we have now plotted the half-lap joint with fasteners in 45-degree arrangement, so fasteners in tension and compression. We again see the quite significant stiffness difference here and a steep load drop, so that indicates a rather brittle failure mode. And now we go to the specimen where we have combined action of 45 and 90-degree screws. We do see, again, stiffness increase very linearly up to a yield point here pretty much. And then we have ductility out of our shear connections or shear fasteners. The other system with this similar setup, fasteners and shear and tension, performed a little bit weaker. The kink is a little bit earlier here, so we get yielding of the fasteners a little bit earlier. A little bit less ductility too, and also less ultimate capacity. This setup here, the red line, indicates the system where we have butt joints with fasteners and shear and withdrawal. So we again have this compound 33 and 45 degree screw-in angle. We get probably we do get the highest capacity out of it. Some ductility here in the horizontal line, however, that is not a lot if we consider it against the shear connectors here. However, if we look at this very stiff connection system here, we still get about maybe a 1/4 inch up to 1/2 inch at the most of deformation out of our entire system. The thick red line here now is the butt joint with fasteners in plane shear action. We do get a very high capacity out of it, and we do also get a reasonable amount of stiffness, of ductility out of the system. Now we want to go, in the last 10 minutes of this presentation, we want to go into the results and statistics that we have obtained from our testing. So the first few tables will look at the ultimate data obtained in a fashion that we present the maximum total force, the maximum force per connector. So this is basically the force per screw. This is the force per connection. So if we had 8 screws in this particular setup, this value times 8 would give you the total maximum force. We have also determined the yield force. The yield force of the system is basically what you want to verify against your design procedures you're designing. If you follow the Johansen yield theory at the yield point, I believe if we look at the predicted load, this should be at around 500 pounds, I would say, somewhere in that range. And here we actually see at a yielding of the system at 900 pounds. We have also recorded the maximum displacement, the displacement at the yield load, and then we have determined the ductility value out of these systems and give you stiffnesses at the load range between 10 and 90% and the load range between 10 and 40%. Here we have the negative load cycle. We present the same results. Positive and negative load cycle had different capacities, as we saw in the load displacement curves already. This is what you see in those tables here to verify which load cycle you want to take for design. And then ultimately in this slide, we present the average test results. So this is the average basically out of 3 dynamic tests of each connection setup, and then averaged between positive and negative load cycle. In a more graphical fashion, we present differences here. Again, positive and negative load cycle had different capacities. The green bars are our positive load cycle and the gray bars are our negative load cycle. And we can continuously see that all negative load cycles had lower capacities compared to the positive load cycles. Cost always plays a role. So we have attempted a little bit of a cost comparison here for the connections. This is just considering the fastener cost. We can see throughout the entire series 1 to 6, we have fairly similar cost comparisons here because the fasteners behave similarly, shear and combined actions of shear and withdrawal, and we get similar capacities out of the systems that are in the similar cost ranges. We have one little extra connection here, that is the butt joint with 45 degree screws. So 45 degrees, 90 degrees to the shear plane, however 45 degrees to the face of the panel. We do see that we have a significant amount of cost here. This is because we compare the cost of one screw to the design level of one screw. So here we saw that we have significantly underestimated our design capacity compared to the test capacity. I do believe we saw overstrength factors of around 8 or 10 even. We will go to that in one of the next slides again, and that basically gives us this huge cost disadvantage of this system. Ultimately, we would need to look at all these connection costs together with the CLT manufacturer. If there's CLT manufacturing companies listening to that webinar now, we are interested in looking at the cost of manufacturing in your plant half-lap joints, surface pline joints per foot of connection or per panel or whatever you want to base it on to come up with a better cost comparison for the CLT connections. There might be a good opportunity here to be more cost competitive by selecting our connections very early in the design stage already and then ask the structural engineers to try to make the system work with the particular low-cost connection. Comparison between static and cyclic performances. So again, for the cyclic performance, we used Curie loading procedures. For the static loading design, we used this loading procedure where we load the specimen up, unload it, and then keep loading it until it ultimately breaks. In terms of capacities, we basically see a reduction of capacity between static and cyclic loading. This is pretty much what we expect. We do see a capacity drop of around 30% all the way down to 7% for the butt joint. For the yield point, we see similar drops between 30 and 17% or 8% in this case. These drops are as expected pretty much. There's nothing surprising about this too much because the cyclic loading will always cause some lower capacities and lower performing connection systems. Performance comparison. Under performance, we basically compare the ductility and stiffness again. So ultimately, we lose ductility in the cyclic testing, some specimen more significant than other specimen. And we do also get a stiffness drop in our system under cyclic loading. Now we want to compare what I mentioned already in the cost analysis. We basically have our design load, our predicted maximum force per fastener using NDS design procedures or the American CLT design handbook procedures, and then we compare this against our test values. We do see overstrength factors all the way up to 9, which is for the butt joint. So some of the design procedures here for the butt joint do not necessarily, they yield very conservative results, however not the most cost-efficient results. Realistically, we are looking at overstrength factors of 2 to 4. Somewhere in that range, I would consider these design procedures here as reasonable and cost competitive. In a more graphical fashion, this looks like this. So again, the butt joint is a little bit of an outburst here. We are very conservative with our assumptions, so we may need to adjust our design factors and design capacities for this particular connection setup, which we can through this test data. So we can basically say, okay, our design times 2, design capacity times 2 pretty much still gives us this overstrength factor of 4, which is considered in the reasonable ranges. All other connection systems provide us with a reasonable amount of overstrength factors. In conclusion, as a summary to this webinar, we will probably need another 3 to 4 minutes and then are ready to take some questions in the chat or by email after the webinar. We were aiming for around 45 minutes of presentation here and we are getting pretty close to that. To wrap up this presentation in conclusions, our tests basically indicate that we do get ductile performances in static and dynamic loading if we use self-tapping screws and plane shear actions. Also, the tests indicate that with connections in withdrawal applications, where we have fasteners in withdrawal applications, fully threaded wood screws in particular, we do get more brittle performances with much higher stiffnesses. However, still what we see here in this particular setup, we still get around ½ inch of displacement while roughly maintaining the load that we have. And again, I want to point out that our design load is probably somewhere in this area. So we have the typical overstrength factor here of 2 to 3 in our system. We do get very moderate performance with self-tapping screws in combined action. Combined action is 45 and 90-degree screws in one setup. We have a large amount of ductility and a very predictable performance of the system in the linear ranges and beginning early cycles of the testing. We do also see that all tests indicate a capacity and stiffness reduction basically in the cyclic loading. There are some exceptions, of course. However, the general trend is that we have a capacity and stiffness degradation in our cyclic testing. The butt joints, as we mentioned, exhibit a very nice performance. We almost get 2 inches of displacement while we are maintaining our load. In the linear design ranges where we actually design now is probably somewhere here between 200 and 300 pounds in design load per fastener. And we can see that the fasteners can take about 1,500 pounds per screw in that particular setup. So we would need to adjust the design procedure here again to get into more cost competitive areas somewhere here or even higher up. In addition, we saw that our butt joints with fasteners at 45 and 30 degree arrangements, so fasteners in tension action, do exhibit high stiffness, high capacity with somewhat of ductility. I'm saying somewhat because the connection is considered very stiff, but still exhibits around ½ inch of displacement before we ultimately fail the system. All the testing basically confirms the conservative nature of the design procedures that we have attempted to use for this, from the American Wood Council CLT design book, the Canadian CLT handbook, or NDS or CSA standards, depending on which country you're designing in, the United States or Canada. So we do have conservative results for all these test setups and design proposals. Some of the connections are, however, a little bit too conservative overall, and then we lose cost efficiency on the system, which we of course are trying to avoid, to be more aggressive on our pricing with timber structures and more competitive in the market. A quick outlook, what we will do in the near future. We could not get any conclusive results on the group action factors for these tests, so we used 8 or 12 or 10 fasteners per system. However, there was no conclusive result on the group action factors of it. Some specimens showed that there are group effects, some specimens showed that there are no group effects, and we will have to do a little bit more testing on this. Dynamic loading needs to be confirmed. Remember, we did create this horizontal prying force here in our load cycle when we are pulling up. So we need to confirm this testing with a small test series and see if we can maintain the results that we have. However, again, we do believe that the results that we have here are usable and presentable and are a very good verification for the design procedures we have. The impact or difference for the 45-degree butt joint needs to be investigated. We need to figure out the difference between partially and fully threaded screws. In this particular test setup, we have used fully threaded screws, which exhibit a tension force in this direction here, as we explained earlier. So we get high capacities out of these systems. However, we are not allowed to use this by the design procedures that we have attempted to use for this verification. So we might need to do some adjustments or potentially look into European design equations that do allow you to use this so-called rope effect on the fasteners. We will also do some medium scale testing with 4x8 cross-lamp panels for instance, shear wall applications or diaphragm applications. The small specimens that we have used now are about 4 feet or 6 feet long. Overall, and we only have an area of 2 feet where we actually have the connection. So we are attempting now to do more full-scale testing in 4x8 CLT panels and see what the system factors are and if we can determine some reasonable design values for shear walls. Also, we further need to investigate the fastener diameter and the influence that comes with that. Self-tapping wood screws are available in 1/4 inch diameters, 5/16 inch, 3/8 and ½ inch, and also 9/16. So there's very big fastener diameter differences, and it might be the most competitive, cost competitive to use a 5/16 inch fastener or ½ inch fastener, depending on how the capacities are. However, we can already confirm that you would need to drive in a lot less ½ inch fasteners than you would 1/4 inch fasteners, and that might reduce installation time on site and overall increase cost competitiveness. Now, ultimately, again, we want to do some and express some special thanks to the researchers that are working on this project, Dr. Thomas Tannert from the University of British Columbia and Afrin Hossan, a PhD candidate at the University of British Columbia. Without the support from the university, the expertise of the professors and the hard work of students, these projects would not be possible in terms of finance. So greatly appreciate the support of the universities on this. And with this, we also want to thank all the attendees that have taken the time to look at these CLT connection systems under dynamic loading. Again, we have the webinar from earlier in 2015 still on the website, which if you're interested, you can take a look at it. This webinar will be on the website as well, and you will also receive a copy of the PDF slides in your inbox sometime today or tomorrow. Then from my end, I believe this is it. this is all the results that we wanted to present and have for now. There's more research coming, which we will likely present in a webinar by the end of the summer. Some interesting research is going on the performance of pre-engineered connection systems under varying moisture content conditions and so on. So we will be presenting on this as well to provide concealed pre-engineered systems for our tall wood buildings in North America. So now I want to thank you again, and I believe this is it for now. If there are any questions, feel free to email me the questions, or I believe you guys can also ask questions in the chat. So we will be around for another few minutes and then shut down the webinar. Thank you very much for your attention.
So Max, we do have quite a bit of questions on the chat. If you scroll down the attendee list, you'll see some question marks. You can click on that and you'll see the questions.
Okay, I'm back here. I can see the questions now. So there's one question here, if there's a handout available. Of course, like, these slides will be sent to you. We are attempting to put this into a more appropriate design package as well, which will be another few months until this is completed, but then you will definitely be invited to download a design copy of these slides and a research report. Then we have a bunch of questions here on the failure modes of the systems. So ultimately, we always get a lot of wood crushing, a lot of wood fiber being pulled out and teared, compressed, which likely indicates energy dissipation and so on. Ultimately, maybe after 15 cycles, bending the fastener back and forth, we did also see some breakage of the steel fasteners and then ultimate failure of the connection systems. The system that has high stiffness in the initial phase is basically a fastener in tension, and then as soon as the fasteners give up the tension load and transfers the load to the shear fasteners, we do have the shear fasteners deforming, yielding, crushing wood fiber again, and so on. So whenever we see the load displacement curves having a high initial stiffness and then a large amount of deformation, this is a combination between tension screws and shear screws, where the tension screws are obviously a lot stiffer element. They attract the load first. As soon as they start failing, they give up the load to the shear screws, and then the shear screws crush wood fiber and deform significantly and provide the large amounts of deformation that you saw in the charts. Yeah, and there's one question here, one comment here, also on projecting the positive curve to the positive static curve into the negative area. Yes, we are aware of this and appreciate this comment. And we basically have done this just to show like a somewhat of a reference line. And we do present the results of the positive and negative cycle in table format, so we can clearly see what the actual differences between positive and negative cycle are, and then can do a manual comparison between the table ultimate load, for instance, and the static applications, and ultimate load and the positive and negative cycle of the testing. Comment here is provided that we should differentiate the colors of positive and negative lines. That is a very good idea, and we should definitely consider that for further published files. Here's one question about the surface pline material. So the surface pline material is typically just a standard plywood in a variety of thicknesses, 1/2 inch, 3/4 inch, 1 inch, or you can do 2 1/2 inch and double it up. Typically, we have used 3/4 and 1 inch standard plywood that you can use buy in any hardware store, we do want to do these systems and test the connections in a fashion that everyone can basically go to a hardware store, buy a sheet of plywood, cut it into splines, and then use that. So we have not used any special material in the surface spline. No, there's one question on the lever arm here. In the dynamic loading, no, we did not use any compensation for this. This is basically why we also created this prying force. We did not have considered the eccentricity of the system in the load application to our center of the fastener. However, if you draw a vertical line down into from the upper load cell to the lower load cell, basically, you will see that they go right through the center of the connection, and there should not be much eccentricities there anyway. There's questions on fastener spacings here as well. Fastener spacings are as per CLT design guide. If you go to our website, there is a CLT section and a CLT connection design guide. The fasteners that the connection spacings or fastener spacings that we have used comply with these suggestions, and as we can see, there was no splitting of the wood observed really in the CLTs, not even if we drive the fasteners in on the minimum spacing. This is pretty much what we expect. The CLT has cross layers, so the cross layer prevents the other layer basically from entirely splitting apart, or at least it reduces the splitting tendency of the system. There's one question here if the bending yield strength of the fastener has an impact on the results. I do believe so. They are the higher the bending yield strength basically gets, the more brittle the fastener is. So we try to get the fasteners hardened to a point where they provide a high bending yield strength but are still able to bend. If you use like cheaper fasteners, for instance, and you just bend them like 10 degrees, they snap apart very easily, and typically those fasteners have a much higher bending yield strength than our fasteners have. I do not necessarily believe that this is a great performance. If the fastener is so hard and so brittle that it snaps at a small deformation already, we could create dangerous failure modes as well. So we prefer to have a little bit more expensive fastener, a little bit more expensive hardening process, but therefore we get a lot of bending out of our system.
Max, we do have a question from Robert on chat, so I will unmute Robert.
Yes.
You can go ahead, Robert.
I don't have anything if you're looking for me.
Yeah, I can't hear any question now.
Robert, we heard some noise. Would you like to try to ask your question again?
No, I don't have a question.
Oh, you don't have a question? Okay, perfect.
Maybe I raised my hand accidentally here, but no question.
Okay, great.
Perfect, no problem. Thank you.
Better, makes our life a lot easier.
All right.
There's one question here from Kyle Sullivan. Kyle is, if I may mention that, is a master's student at Oregon State University, currently conducting testing on CLT connection systems as well. Thank you, Kyle, for participating and engaging with this test project. There's the question if plywood orientation matters. I do not believe it matters for the surface Pline systems, because in the plywood we also have the cross layers basically, and regardless of which way we have it, there's always a certain amount of layers engaged perpendicular and parallel to grain. So overall it should average out, and I do not think there's a specific capacity gain or loss of these systems. Okay, now we still have a bunch of questions here. Some of them will take a little while to answer. I will try, like people that have asked to get an answer by email, I will try to answer these questions by email. Again, I want to thank everyone that has participated. I hope it was interesting and gave you a little bit of an overview on the performances of these connection systems. And now I wish everyone a good day and successful CLT designing timber structures in the future. Thank you very much for your attention.